Sure. My name is Ivo. I'm a postdoctoral researcher in Thomas Lab, and I'm here since February. And before that, I was working in Italy for 6 years, and I was doing my PhD there in neuroscience or neurotechnology. And today's exercise, which is my first exercise, is very easy and funny actually, because it's, in my opinion, the coolest stuff you're getting taught in this place. And I will also give you a cool real-life examples, which I was doing with some human amputees. Some of you heard it already, like the stories with the experiments. The exercise is called peripheral nerve interfaces, and I think you're going to have a mini exam like next week on this. But it's going to be easy because this is very non-complicated. There's no formulas, so sit back and relax and enjoy it. So some of you know more about it, some of you know less about it. There's the nervous system, right, which we need to control our arms, our eyes, our organs and everything. There's an autonomous nervous system, which is doing everything without your control. And there's the controllable, the somatic system, which is responsible for movements, for example, like your arms. Now, there's the central nervous system and the peripheral nervous system, which you heard about, I guess. And my question for you is, what do you think is the brain central nervous system or peripheral nervous system? If you think central nervous system, raise your hands. If you think peripheral nervous system, raise your hands. It can be both, but it's not. It's central nervous system. What about the spinal cord? Do you think the spinal cord is central nervous system?
Yeah.
Skepticism? No, that's good. That's true. And the other nerves which are in your arms, which are in your eyes, everything which is peripheral is obviously the peripheral nervous system. Now, the first question is, what's the difference between these two and why do we have to differentiate between these two? Now, the central nervous system, the brain and the spinal cord, are responsible for processing information, and it's like a computer. So everything, all the information which are coming from the outside have to be processed by the brain and then translated to actions. So, for example, controlling your hand, controlling your eyes if you're tired, controlling your organs, right? And the peripheral nervous system comes from your organs to the central nervous system and the other way around. So everything in the peripheral nervous system is connected to, for example, sensory cords in your arm or in your feet when you need to feel sensations, or in your eyes if you see something, the peripheral nerves transport it to the brain. Now with the eyes it's a bit different because the eyes are very close to your brain, but still the nerve between the eye and the brain would be considered peripheral nervous system. And I want to give you a few examples about this. Now, what's clear is you have the central nervous system, which you see here in the middle. You have the spinal cord and the brain, and you have the different organs. So you have the lung, you have the different, like your arms, your hands, your feet. You have the liver, the stomach, your heart, which is also very important to control. And you have, for example, the bladder and the glands. So the glands are responsible for hormone production. And these are all controlled through, you guessed it, the peripheral nerves. So you have the central nervous system here. Can you see this? Yes. You have the central nervous system, the brain. That's the eraser. Come on. You have the central nervous system, and you have the peripheral nervous system. So the peripheral nervous system starts from the spinal cord. And I want to go a bit into detail regarding peripheral nerves, and especially their anatomy, because it's very important for us as engineers, So maybe you've seen this already. This is how a nerve is like built up. So if you cut the nerve transversally and you look inside of it, an engineer would say, okay, it's like cables. You have a bundle of different cables, like an HDMI cable, and every single filament of this cable is controlling a different sensor. So in your hands, for example, you have pressure sensors, heat sensors, pain sensors, and different other sensors, also on your organs. And from every sensor on your skin, which may be up to 1 million on your hand, for example, one of these axons, so these filaments, is going in direction to the central nervous system to transmit information. Now here you see you have the axons, which are incorporated by the perineurium, which is a strong resistant tissue, which can be like the isolation of your cable, okay? And around these mini cables you have in the inside, so these are called fascicles. You have many intermediate cables, you have the epineurium, which is another fascia, you call it in English, which is containing all of these fibers. And this is very rigid, and it's there to protect the nerves. And it's also very slippery. So if you move your arms, your nerves are getting longer and shorter, right? So this is also very stretchful. So you can actually move the nerve without damaging it immediately. If you have a motorcycle accident, for example, there is this plexus issue, which is classic. So when you fall down, your arm is like ripped in one direction, and it's ripped so far that the nerves are like pulled and they're getting damaged. And these people usually don't feel anything in their hand anymore, and sometimes they can't control their arm anymore, you know? So what we can do as engineers, and that's the cool part, is we can control these kind of nerves, you know? Because the question is, how do these nerves work? Is it through chemistry? Is it through blood? Is it through hormones? Or is it magic? It's kind of magic, but it's electricity. Why is it magic? Because we don't really understand for 100% how they work. What we know is that there is current being transmitted, so we can translate it. So as example, if you, let's see if my animation comes, yeah. Awesome. So you have, for example, these Ruffini bodies, which are around your hair. And they're like this. And from there, you have an axon, which is connected to every single hair. Right? So if you touch the hair on your hand, which is in the periphery, then you feel pressure or vibration in your brain. It's a bit strange. So what we can do is we know that if I touch the skin and the hair is moving, there's an action potential being created, which is electrical current, which is traveling through this cable or through this nerve in the direction of your brain. So what we can do, we can take the cable, and in the middle of the cable we insert a small circuit board to inject current, and then we can modify it, right? And we can also read the current by reading changing charges inside the nerve. And that's how we can interface with the nerves. And then there's, for example, also the nociceptors, which are the pain receptors. So if you put your hand on the oven, it's going to hurt if it's on. So what's happening is that your nociceptors are feeling the pain, and they send electrical current to your brain, and your brain will react and pull back your arm. So that's a reflex. That's where you don't have the decision to pull it away or not. It's going to happen by itself. But this is also through these sensors in the periphery. Now back to the cool guys, the engineers. We have the peripheral nerve interfaces, which are the ones we can create in the laboratory, right? So what we do, we make mini PCBs, printed circuit boards, you can put inside the nerve, and then you can read the current or you can send current inside. So what, like more professionally said, you can do and perform electrical stimulation, which is when you inject current inside the nerve, or you do neural recording, when you read the potentials of these small fibers. And the problem may be that when you do this, you have so many different small filaments, as I said before. For example, let's say you have 250 in one nerve, that you would need 250 small contacts to connect to all of these small filaments, right? Which is very difficult, because one of these filaments may be as thick as a hair, or like half of it, you know? So it's very hard to get electrical contact with these. What I want to say there is that we have 3 subgroups, which may be part of the test or not, I don't know, because I have never seen it. There's non-invasive interfaces, semi-invasive interfaces, and invasive interfaces. Now if you talk to a medic, or you ask the Oxford Dictionary, and you ask them what does invasive mean, invasive is everything you put inside your body, so a tablet or under your skin, or you make an incision and so forth. On the neuroengineering side, it's a bit different, because we only think about nerves, right? So I don't think about the rest of the body in this term, but I only see the nerve. So as soon as you put something around the nerve, you think it's invasive or non-invasive. Invasive, raise your hands. Non-invasive? Yeah, that's right. So intelligent guys. And then there are semi-invasive interfaces, which are a mix between 2 of them, which I will show you in a bit. And then there's very invasive interfaces. It's the one you put through the nerve, right? Because you can't be more invasive than that. Well, yeah, you can cut it, and that's like the most invasive thing you can do to a cable or to a nerve. So when we talk about nerves, it's important to consider that cuff electrodes, for example, which are going around the nerve, are non-invasive. So that's, for example, a cuff electrode. As you said, it's non-invasive, so it's a layer, a round layer of silicone, usually, with different exposed metallic contacts, which can be gold or platinum iridium, and you put it around the nerve, and then you see here, for example, you have 4 different contacts on this cable, right? So you can use these 4 contacts to inject current into the nerve or to read current outside of the nerve. But if you have 150 filaments and only 4 contacts, you cannot do that much, right? So if you have one nerve which is going to all of your palm and you have 5 fingers and only 4 contacts, you may activate only 2 fingers, all of the hand, only the bottom of the hand, depends what you do. Then you have the cuff electrode, which I talked about already. That's just a different model. And there's also commercially available cuff electrodes, as for example from Otto Bock. So you know Otto Bock, maybe it's a company which is doing prosthetic devices, so it's doing leg prosthesis, arm prosthesis, which can be active or only passive. Now in the case of active prosthesis, you have this cuff electrode which is stimulating a nerve in the leg, which I can't remember what's it called. So there's people that have a lesion of a nerve leg, and when they walk, they can't lift up their foot like this, right? So this movement is not working. So what happens is that they're falling down all the time because they or have to lift their leg like really high in the air, or they're getting inciampato, I don't know in term, or English, how do you call it? So what they're doing is they're doing gait analysis of your walk, and every time you're doing a stride, you get stimulated in this nerve and your leg lifts up. So that's happening automatically most of the time. So patients can walk again, you know. That's, for example, a non-invasive example. Then you have the flat interface nerve electrode, short FINE, which we may hear about because it's a very famous device. And this is like a cuff electrode, but only that it has a defined shape, so it's already flat and it's not round as the nerve. So if you implant it on a round nerve, the nerve will be like pushed together and will become flat. And the idea of this is that you increase the neural selectivity. So you still have 4 contacts, for example, but since you're pressing the cable together, or the nerve, these 150 fibers are distributing. And they're like maybe grouped, right? That makes sense? Yes, no, maybe? Yes. So you can stimulate different groups of nerves, and you can be sure that you stimulate single fingers, for example, only, you know. And then you have very invasive electrodes, which we implanted in the human amputees, which are the time electrodes, which were developed here in Thomas Stiglitz's laboratory about 7 years ago, I think. And we're actually still working with these. Now, with these electrodes, you have, of course, higher neural selectivity, because if you look at the nerve from the cuff electrode, maybe, let's say you have 150 of the fibers here, right? And you have 1 contact, 2nd contact, and 3rd contact, and number 4. So that's the cuff electrode, which is semi-selective, because if you stimulate here, the electrical field will be something like this for each contact. So that's the axon group you're activating. If you use the intraneural electrode, you will have this small PCB with single contacts. And since it's inside and the outside of the nerve is isolating, you can actually apply smaller current. So what you see is that you will activate smaller axon groups and smaller fiber groups. So the chance that you will activate single sensations on your hand is getting bigger with the increment of the contacts. So that's really important here. And that's the electrode we implanted in 4 upper limb amputees. The first one had it implanted for 1 month, and then we had 3 more amputees who were arm amputees. They had these electrodes implanted in their upper nerves from the hand. So you know the ulnar nerve, which when you hit it on the desk hurts a lot, which is responsible for these 2 fingers. And then you have the median nerve, which is responsible for these 3 fingers. So we implanted these 2 nerves with 2 electrodes each, and then we were injecting current to see what the patients are replying. Because the only body who can tell you how he feels is the patient itself, right? So there you see on the right side how big it is, more or less. Currently, they're not used in clinical studies anymore, but we're translating them to a fully implantable system. So now there's a small break, and then we will implant the same thing in patients with a pacemaker. So everything is inside, because before, as you will see in the video, the cables were still coming out of the skin, right? And we had to attach to them every time we were doing experiments, which is not such a great advantage, of course. So there you see a bigger image. And here you can see, for example, the small contact. And this electrode has a total of 14 contacts inside the nerve. And here, there's a suture thread which you can pull through the nerve. And that's how you implant it, like usually neurosurgeons. And with this electrode, we also did stimulation of the nerves, but also recordings. So the stimulation experiments were quite straightforward because they had a myoelectric prosthesis, so you can control it by opening and closing it. And the moment you touch something, through a microstimulator, embedded systems engineering and stuff, we send electrical stimulation through one of these contacts, and we test all of the 14 contacts, and we see what happens. Then we ask him. He says, "Okay, I feel something here. It's vibration." And we say, "Yeah, it's cool. Let's save it." And we try it again the next day. And if he says, "No, it's more like pain," then you don't use it anymore, or you change the parameters. And when you do recording, what we did is we gave him the prosthesis. He was grabbing objects, and the moment he grabbed them, we were watching the neural activity. We recorded it, we saved it, and we tried to feed it back into the electrodes to give him sensation back. And now the cool stuff, because I have videos. So that's the first patient, Dennis from Denmark. And this was a clinical trial for only 1 month, because the thing you have to do when you want to translate this kind of devices, first you do animal experiments, you go to the European Union, you say, "Look, this is working." Then you do large animal studies. Then you do short studies in humans, 1 week or 1 month. Depends on how good you are in writing projects and how friendly they are. And then you do long-term studies, which we did for 6 months. So as you can see here, he was holding a cup, for example, and you had pressure sensors in the fingers, and the pressure sensors went to a really big computer, which you don't see in the picture because it wouldn't be cool. And then he was stimulating through the cables which came outside of the skin, which you don't see because it wouldn't be cool. So we put like fascias around, and that's for publishing purpose. Yeah, there you can see it a bit more closer. And the patients were controlling the prosthesis with EMG electrodes. So you put the EMG electrodes on the surface of the skin, and when your muscle activates and you do this movement, which amputees can still do, only that you don't see the hand, you record the EMG signal and you open the hand, from like the robotic hand. So this was like the closed loop in the embedded system, and this was like the idea. So of course, you want to know how this electrode is being produced, because we make it here and it's amazing, and it's really amazing. Jokes. And what you can see there is that we're using wafers of silicium, which is called in English silicon. And on the silicon wafer, we create layers of non-conducting polyimide, which is like plastic, basically, And in between, you put metals, as platinum, for example. And this is a clean room process which takes about 2 to 3 weeks. And you have to plan it very carefully. And sometimes things are going wrong because the environment is not clean enough, or you're changing temperatures, or the machine is changing, or somebody else is changing. And at the end, what you can see here is the electrode from the side. So you have the plastic layer around, which is insulating, so it's not getting in contact with the skin. And you have here an opening, so this should be open, where the platinum, in this case, can get in contact with your nerve fibers. So you can also decide how you make this electrode, and that's awesome because you can use CAD software, and you can really draw based on the nervous transactions you're having. So this is, let's say, quite artistic actually. And there you see how the time electrode is implanted. So what you do here, again, you see the different fascicles. So the fascicles are containing the different fibers, and it's like the subnerve. And you see there's different fascicles, and we want to target these fascicles by implanting the time electrode. And what you do usually is you pull the electrode through the nerve with a needle, and once it's inside, you fix it, and then you can try to stimulate the nerves. And you can do this after 1 day. Question?
Yeah. How severe are the body reactions to the electrode inserted in the nerve as the nerve
Yeah, it's a good question. Plus point for this. I write it down. But it depends a lot on the electrode. You know, if it would die, you could never implant this. So when they were doing animal studies, they showed already that the nerve is not getting harmed. You know, or that the weight between advantage and disadvantage, like tissue damage, is so big that it's worth implanting it. So if you use the cuff electrodes, for example, with all electrodes, you get fibrotic tissue reaction. So it's like a Narbe, you know, Narbe? Yeah, like a scar. And this happens anytime you put a body from the outside, like a foreign body, in your body, right? Because your human body says, okay, that's not my stuff. It's hard, it's electronics. I don't like this, so I'm making this capsule. And it's basically like scar tissue. So it's like isolating the electrode. And this happens with cuff electrodes, so the non-invasive ones, with the semi-invasive ones, and with the really invasive ones. And that's actually a really big problem for us. I'm going to answer your question. Because you have the electrode with your contacts, right? And you have your small axons, so the fibers. And if you have no foreign body reaction, you can stimulate and you will have this kind of electric field. The moment you get some kind of body reaction, which is like fibrotic tissue, which is not conducting because it's isolating, it will be harder to reach this kind of electric field, right? So you have to inject more current, and the electric field will be a bit more different. So maybe it has to be larger, or it will not be the same. And this happens actually over 6 months, and after, at some point, it will like slow down really a lot because the body is giving up. He can't like put it out because you implanted it really deep inside. So it's like calming down and taking it as it is. And first you have to wait for this point. And that's actually bad because it means the first 3 months, when you inject stimulation, it will change constantly. And that's not good, right? Because you have to stay behind the patient all the time. And maybe one day it's pain and the other day it's like vibration or something. So there's a video. Let's see. So that's the first patient, I guess. Yeah. So there's no blood. That's our neurosurgeon. And there you see how the time electrodes, so the very invasive electrodes are implanted into the nerve. So you had to make a skin incision, which was like here and muscle height, to access these two nerves. Yeah, that's the cable. Okay, sorry, it was 16 contacts. The first one had 14. Today we have 18. So you open the skin and you insert the electrodes into the nerves. And what they were doing here, you see 2 different nerves. We implanted 4 electrodes. So 2 on the ulnar nerve and 2 on the median nerve on this height. And the amputation was here, here, or here. And there's the small stimulator. And there you see the stimulation. Yeah, so there you see how Dennis is putting on his prosthesis. So on the top you had the cables coming out, and on the bottom you have the prosthesis. And you see also the hand is very small, light, and handy, because it's a research hand. So. But it worked. So we also let him take different types of materials. So you see there's a glass or a plastic cup, which have different compliance. You know, so one is more soft, the other one is less soft. He didn't see anything, he didn't hear anything, and he should like understand which object he's touching at the moment. And he told us, and then we wrote it down. Sounds easy, right? Okay. So there's a video from the experiments we performed after this. So this was the 1-month trial, and in there we had Fernando. He was the first patient who had an implant for 6 months, and it still worked after 6 months, which was cool, but I can't do anything wrong. Yes. So he was still using the same hand. He had an amputation which was a bit higher, and you can see there, for example, he's grabbing a ball and then a cylinder, and I think we also had a triangle, and he was doing the same tests but a bit more sophisticated. You know, so I actually made some 3D printed objects which have different compliance. So one was soft, middle soft, and very hard, and he was doing the same test with specific objects, so we could measure how hard the objects were, and then, you know, write down precisely, like engineers should do, in the paper what he was doing. There's also me without hair, young. And next. Okay. Then we have this is the very most invasive electrode which there is. So there was the one which you insert transversely through the nerve, and this is a regenerative neural electrode. So this you can use when you cut the nerve, for example, with the plexus accident of the motorcyclist, and it can also happen to bicyclists. And you take the two nerve endings and you put it in this channel, which is made of biological compatibility materials, which can be cells from crabs or anything which works, and you wait until the nerve grows back together. And inside you put again this kind of electrode contact. So this one had I think up to 120, and the nerve is growing through the holes, right? So it's a bit different because you have one nerve ending, you have the electrode, and you have the other nerve ending. So this is like the arm, for example, and that's your brain and the peripheral nerve. And there you have the electrode with different old contacts, which are all connected to cables. And you hope that the axons, so the filaments, are growing through these holes and coming out back there. And then you can simulate all the single filaments. In theory, it's all amazing. And if you do it practically, it's not so fun anymore. Cutting the nerve, placing stumps. Yeah, we know this. Yeah, and then you have the needle-like electrodes, which is called the Utah area. I think one of you was asking a question before, or he left. I don't know. That's simply an area of many needles. You just shoot inside the nerve with a pressure gun. So it's again a bit different because if you look at the transection of the nerve, you will have needles here everywhere in the nerve, and there you have your active contacts to stimulate the fiber. And that's also bad because, I mean, you're piercing a nerve with many needles, which at the end you need to be highly selective. And that's a really big problem because at the end, what we learn is we have a cuff electrode, which doesn't harm the body, so it's non-invasive, but it's not selective. And on the other hand, we have these kind of electrodes, which are highly selective, but also highly invasive. Now you're asking yourself, what do we want? It's a good question. We want the electrode, which is highly selective and non-invasive, right? Does it exist? No. So there's a lot of work to do, and if you have ideas, you can write me. So at the end, if you look at this plot, you see the different electrodes we were talking about. You know the cuff electrodes, which are not invasive, but they're not selective. And on the other hand, we have the Utah array, or USEA, which is ureter slanted electrode array, and the sieve electrode, which is the regenerative one, which are highly selective, but also highly invasive. And then in the middle you have the time electrode, which is the intraneural one, which I showed you before, which is very important because it's from here, so it's the best, which is like semi-invasive and semi-selective, okay? And now, yeah, okay, this I told you. It's my favorite slide. Final question. You know this guy? It's the new one. There was the old one, which was, what was it called? The old guy who was doing Wer wird Millionär? My generation. Yeah, man, he's the best. But I thought I put the new guy because maybe you know him more. So, you don't know him? Okay. So my question to you was, I was curious because you had lectures about pacemakers, right? The last two lectures. So I wanted to ask you, do you think that a pacemaker is a neural electrode or could be considered to be a neural electrode? Who thinks it's a neural electrode? Who thinks it may be a neural electrode? Who thinks it's not a neural electrode? Yeah, okay. So what do the others think? No, but actually, I mean, if you think about it, it's a very difficult question because at the end, what the pacemaker is doing, you put it inside the chamber of your heart and you stimulate the liquid inside your heart, so the blood. And through the blood, you stimulate the muscle of the heart, right? So actually, you're directly first stimulating the muscle and then consequently, of course, you're stimulating the nerves. So I wouldn't say that it's a neural electrode. If you implant the same thing in the nerve, then it would be a neural implant. So it's just about like definition, actually.
But wasn't this muscle tissue in the heart that you stimulate?
Mm-hmm.
It has this leakage current, so it kind of acts like neural tissue.
The liquid?
No, the muscle.
Yes.
The muscle tissue usually sets this leakage current that if it's still working correctly, it acts like neural tissue and has this action potentials that your heart is beating.
If you stimulate,
No, if you're not stimulating.
like in a healthy,
if it's working.
in a
Like
healthy
in
person,
pacemaker,
yeah.
the muscle tissue there has this rhythm of creating its own action potential.
Yeah, that's true, because it's traveling along the
I
muscle.
read, I don't know,
Yeah.
I guess in the slides, that it acts like muscle tissue but also like neural tissue.
Hmm.
That's
Because
what
it's
I-
conducting. Yeah,
Yeah,
but it
it's
makes sense actually. It makes sense also, because if you stimulate normal muscles, you have like a nerve which is going to the motor neuron, and the nerve is going to one muscle. Like one fiber is going to one muscle cell and activates one muscle cell. But in the heart, it activates one muscle cell, and it's a mixed muscle, right? It's like striated and glatter, so glatter und
I don't know. Could be.
like you can control it, but you can't control it, something like this. Makes sense. It's not a question because I invented it, so don't worry. We can ask Thomas, but I thought it was fun. And then we have one last thing, which was also in the presentation. How long are like exercises lasting usually from presentation?
45 minutes.
Ah, okay, not half an hour. Okay. You have these. You have these kind of almost peripheral nervous interfaces, which are also correlated to muscles again, which is really interesting because it's kind of a mix, and it's also used to control neuroprosthesis. And it's called targeted muscle reinnervation. Did you hear this already in some other presentation? TMR? No. So basically what this guy was doing, Todd Kuken, very intelligent from the USA, he was connecting the arm nerves of the amputees to the breast muscle, you know, the abs. And from there you can read EMG signals. So the moment you move your arm as amputee, your arm is not moving anymore, but your muscle, your flex muscle is contracting. And especially single fibers of the muscles are contracting. Like, did I explain this clearly? If you're silent, I'm gonna try to explain it again. So
Isn't it because sometimes the amputees have pain in those nerves?
also, yes,
And
yeah,
then you could stimulate them and I don't know.
then it stops.
Yeah.
But this actually makes it bigger. So that's a disadvantage. So that's what's written in the slide. So you have the arm nerves and they're like free floating, right? So what happens with the nerve, it continues to grow because they want to go back to their arm, right? And they want to grow back into their fingers because they're reproducing. But they can't because the arm is cut. So they're making these bulbs, which are called neuromas, and they're getting bigger. So you have a big ball of nerve in your hand, and if you touch it only slightly, it can be as painful as a tractor going over your feet. Like I didn't experience this, but I think it's more or less like this. What you can do is like you can cut it out, and then it will stop, but it will most probably grow back. So what they were doing is they take the nerve endings, they suture them to the muscles, the flex muscle, and on the muscle they put EMG electrodes. So you record the contraction of your breast muscle, no? And you use this EMG electrode to control the prosthetic arm. So you can naturally think of moving your arm and it's actually happening. Okay, so that's cool on one point, but it's not really a neural interface because you're actually only recording EMG signals, so muscle signals, but you're doing a neurosurgery. That's why it's kind of almost peripheral nerve interface. And the biggest question here is, of course, why do we need this actually? I mean, why can't you just put the normal arm prosthesis on your arm from Otto Bock, which have two contacts here and two contacts here, and you can open and close the hand, because if you do things, you want to do more movements than opening and closing, you know, which you never realize. Because if you use a prosthetic arm and it's stiff, you cannot go to your computer and just turn it and then do the work with your single fingers. But you have one thing which is mostly hanging out here, and the newest prosthesis, they can like turn or open and close, for example. But it takes a long time because you still have two contacts. And there you have like more contacts, so you have one nerve and one muscle fiber for each single movement. So the patients can actually like kind of do different movements and also move their elbow and their shoulder, their wrist and their fingers. So there you see a picture how it works. So they usually map this type of muscle and they decide where they put the nerves from the arm, so you see it's amputated, and they just put the nerves onto the single areas. And then they ask the patient to simulate the hand opening, and they record all of these, I don't know, it's 50 channels, and if one channel is lighting up, you know, okay, if I ask him to move to open the hand, then this EMG finger, this EMG location is like activating. So I connect it to the prosthesis for embedded systems engineering stuff, and then I can move the prosthesis. End of story. Sounds very easy. Of course it's not. And it's also really expensive, because if you look at the patient, you can see that it's very heavy, right? Because you have the prosthetic arm with a lot of mechanisms. You need the battery, which has to last a lot. And you have all the gears also inside. And it's, of course, also very heavy, because it's a lot of machinery. Because if you think about how much your arm weighs compared to your body, what do you think? Is it 3%, 10%, or 15%? Who thinks 3%? Huh? What do you think? Like your arm, how much does it weigh compared to your body weight? 3? 10? 15? I think it's 3. I will look it up on Google. Or maybe not, but then you will remember. I think it's 3. So you have to think about, if you weigh, I don't know, 100 kilos, then your arm is going to weigh 3 kilos. And for such a prosthesis, it would be like not a lot, considering the battery, the machinery, and all the cables. You know? So for a 100 kilo person, and that's very important, because if you start putting prostheses on the amputees which are too heavy, consequently they will get different issues with their spinal cord, for example, and their orthopedic aspects, you know, because they will start to walk like this over the years. And then they have to go to more and more medics, and they cost more to the system, and they're more unhappy because they also get back pain just because they have an arm prosthesis, you know. So this has, the weight of this device has to be tailored very specifically. Then the phantom limb pain you were talking about before is not going away, but I don't know why. And there's no long-term studies. And this device exists since a very long time. So when I was doing my bachelor's, I don't know, 7 years ago, maybe, more or less, then this was already there, and it was already cool, you know. So the thing is, why in 7 years there's no long-term studies? And it can be because of different reasons. So I wouldn't be standing here and saying, okay, no, they can't do it, they just faked it, and that's it, you know. There may be some technical issues they have. Maybe it's the weight, maybe it's the battery life. And there's still some work needed, of course, on this. So that's the state of today. There's no long-term studies, so we can't give it to patients, you know. If it's working for 5 weeks and then everybody comes back like this and they say, like, I can't do it anymore, then you can't sell it as a product from a company. So it's heavy, and it's about the power supply. That's it, guys. It's over. So easy. So next week, the 4th, you have a test. And this is about the exercise of today in lecture 7 and 8, which were pacemakers, I guess. If you don't know, I don't know. Come on.
Pacemaker and